All right. We started working on Monday with force, the idea of force and work, dealing with how much work is being done. Work is a scalar quantity, it can be positive, or I'm sorry, if we just go back and review a little bit, when you're talking about work, everyday work, what we mean when we talk about work, you could be working on your homework, you could be working on a job, we could be digging a hole, we can be moving a big pile of leaves from our front yard to the backyard. We could be moving or splitting wood and stacking it. We could be sitting here doing our homework. That's our everyday meaning. It's physical or mental effort. We put a physical or mental effort into something. That is work. When we're talking about physics, though, physics meaning work is only done if a force is exerted on the object and displacement occurs. Okay, that is when work is done on an object. And if you think about this, if I had an object, okay, and I'm just holding it up here, there's no work being done. Okay, I'm just holding it there because it's not movement. But if I let go of this, the object would fall. If the object falls, work has to be done. Well, what work does the work in that point, or at that point? Well, that's the force of gravity. Gravity is doing work on that object. So work can be done without exerting a force physically by us. It can be done by gravity. Or we have magnets. Magnets, electrical fields, they all can apply a force. And if they apply a force and objects start to move, then work is being done. So anytime an object moves, work has to be done by something. Okay, it could be a person pushing on it, pulling on it, or it could be just gravity. Okay, so how we calculate work is we take our force and we multiply it by displacement. Okay, both of those are vector quantities, Victor. And when we deal with this mathematically, we're going to be looking at a dot product, which is just a number or a scalar. Cross product is a different type of product with respect to vectors, Victor, but work is just a dot product. We have no direction on it. Just basically, the work is done in the direction of the movement. Then we talked about a cart that's on wheels, that's being pulled. We calculated work there. Picking up an object, if we have an object that we pick up, it's going to at a constant velocity. That means we have a zero net force, but we have to be able to apply a force that's going to counteract gravity. Okay, we'll counteract gravity, so we have a force that's applied that's opposite to what the weight is, and we can multiply about that by the displacement of the object at that point. My example on Friday or on Monday was if we just held a book off to the side with no movement or no displacement of it with our arm off to the side, no work is being done. Our arm gets tired, but no work is being done because the object is not working. And that's the basic definition of work in physics. Work, you have to have movement to have work. Now, it is a lot of work to hold the book up. Okay, it's a resistance work if you want to think of it that way. But you're resisting something, but there is no work there because the object is not moved. Let's see. We started talking about friction. Friction can do work. Okay, it dissipates. Well, what friction does, it dissipates the amount of efficiency of an object. When we talk about efficiency, it's work output over work input. Okay, work output over work input, and what happens with our work output is it gets dissipated because of friction. Okay, it gets dissipated because of friction, and that makes our whatever we're dealing with less efficient. We took a look at a block that's being pulled, did some problems, dealt with the idea of work. We pulled one horizontally for 15 meters. Coefficient of friction, we dealt with friction. We had to deal with two different types of work. We had two different types of forces. We have a force that's applied. That is this work right here. That would be like the work input, what we are putting into the object. We're putting in 750 joules of work into this object. That is our work, our work input. Because we have friction, friction dissipates the amount of work, because friction is also a force, and it's also going a distance, but it's going in the opposite direction. So if we went 15 meters with this, there's going to be a force that's pushing against this for 15 meters. Okay, so it is slowing it, or it's working against what our applied force is. So what we have is what we call is a net work by subtracting these two values. Once again, this net work is like a work output. It's the result of work or forces that are combining together that's doing a job. This here is a work input. This is what we are putting into this object. We're putting in 750 joules of work. But not all that work, friction is dissipating some of that work. Let's go down to the next problem. How much work is needed to achieve a constant velocity of a 2 kilogram mass for 5 meters? Mu is equal to 0.1 or 0.2. Once again, for velocity to be constant, okay, for velocity to be constant, we have these connected ideas with velocity being constant that we continue to work with. Velocity is a constant. We have acceleration is equal to 0, and our force net will also equal 0. And you have what is called equilibrium. You have unbalanced force or balanced forces. You have balanced forces, which goes into the idea of inertia. The idea of inertia is object will stay in a constant state of rest or motion unless acted upon by an unbalanced force. Well, if we have no acceleration, it means we have a constant velocity. The object will maintain the same state of motion. We will have balanced forces, and we also call this equilibrium. And all those are connected together. So our force net must equal 0. Our acceleration must equal 0. Our force of friction, if we take a look at our force of friction, it's equal to mu times force normal. Go ahead and calculate your force of friction. Now remember what we had to do. We have a 2 kilogram block. We have weight here and our force normal here. They're equal but opposite, so go ahead and calculate your force normal. And then calculate your force of friction. Test, what does our force of friction come down to?
3.92.
3.92 newtons. And we are pulling this object. How much work needs to be achieved to assume a constant velocity? Okay, for 5 meters. So let's take a look. Our force of friction is 3.92 newtons. Okay, that's our force of friction. If we're maintaining a constant velocity, our force net has to equal 0. So our force applied, Jordan, what does our force applied have to be?
Same thing.
Same thing. So we could probably put a negative with the force of friction. So our force applied has to be 3.92 newtons. Okay, that has to be our force applied. So we want to calculate how much work is required to pull this 5 meters. Well, we have 3.92 newtons applied that's going horizontally. This is how much force that we must apply horizontally to get this object to move at a constant velocity. So to calculate our work, we could take our force times our displacement. Go ahead and calculate your amount of work because we're applying 3.9 newtons. We're going for 5 meters. What is our work that we are doing to be able to accomplish the constant velocity for 5 meters? Riley, what do we have? What do we come up with?
19.6 joules.
Okay, taking our 5 meters times our 3.92 and 19 point, what'd you say?
6 joules.
6 joules. Taking our 5 meters times our 3.92 newtons. Once again, we are not using the net force here because our net force would be equal to 0. If we multiply that by 5, we would not get any work being done. Only the applied force exerted in the direction of displacement does applied work. So if we have a mass that we are pulling at an angle, if we have a mass and we're pulling at an angle, we have a rope over our shoulder, and we are pulling this mass at an angle. Only the parallel force to the surface does the work. The perpendicular force, what this will do is our first perpendicular, this perpendicular surface will increase or decrease your normal force, which will increase or decrease your force of friction. So the force that's going upwards is once again just decreasing the force of friction. Or if I'm pushing downwards on this object, if I'm going down on this object, then I'm going to increase my force of friction. But only the force that's going horizontally does the work. The work that the force applied does perpendicular, the work that does, it decreases your force of friction, which will also help you in moving an object. So suppose we have, that should be 30 degrees. That should be 30 degrees, not 300 degrees. We have a a 2 kilogram mass, we're pulling now at a 30-degree angle. How much work is needed to achieve a constant velocity of the 2 kilogram mass? Well, we are pulling horizontally and we're pulling vertically. We don't know what this force applied is. And that gave us a really difficult problem to work on here. That's okay. We still have our force normal, which is our weight. That's going down, and we're equal but opposite that going up. If we take a look, and this goes back to what we've done in the past, this is our F applied sine of 30 degrees. And this is F applied cosine of 30 degrees. Once again, if we are going at a constant velocity, this force net must equal 0, which tells us our force applied is equal but opposite to our force of friction. Force applied will be equal but opposite to the force of friction. Well, let's look at our force of friction. Force of friction, once again, we have 2 kilograms times 9.81. Okay, but the problem we run into now is our force normal is going to equal to this 9.81, or 2 times 9.81, but we're going to subtract off force applied sine of 30. Because we are diminishing the amount of our normal force by pulling upwards. So our coefficient of friction, or our force of friction, we have to multiply that by our 0.2. So we have 2 times 9.81 minus FA sine of 30 degrees. I'm sorry I put a very difficult problem in here to begin with. Our force parallel has to be equal but opposite. So our force of friction has to be equal but opposite to our force applied. Well, the force applied going horizontally is FA cosine of 30. This has to be equal to the opposite of 0.2, 2 times 9.81 minus FA sine of 30 degrees. Which now gives us an equation to solve for FA. Once again, I should have saved this problem for till maybe Monday to work it together. So we can distribute our 0.2 through. We have FA cosine of 30 is equal to negative 0.2 times 2 times 9.81 plus 0.2 FA sine of 30. This just gives us a nice, messy equation to be able to solve. I know my thought to this was I was going to give just evolve from what we've done up above, but I've just made this much more difficult than I had to. So what we have is we have FA cosine of 30, subtracting off 0.2 FA sine of 30 is equal to negative 0.2 times 2 times 9.81. I'm going to complete the problem just because we started it. I'm a little frustrated with myself. We can factor out an FA. So we have cosine of 30 minus 0.2 sine of 30 is equal to negative 0.2 times 2 times 9.81 and divide by this quantity. Cosine 30 minus 0.2 sine of 30, cosine 30 minus 0.2 sine 30. Once again, I did not mean to make this such a complicated problem, and I did. And we should come down to, I think, 5.1 newtons. So our work is our force applied times our distance. Now remember, the only thing that's doing work is the horizontal force, so we have to take our 5.1 cosine of 30. So we have 5.1 cosine of 30 times a value of 5. Once again, so you should come down to 22.2 joules. The next problem is the same type of problem, but it's pushing downwards. We're not going to go into that today. We're going to leave be what's going to be done here. We'll just leave it at that. Once again, I apologize for throwing probably too much at you at one time with that problem there. That's the type of problem that we eventually evolved into, and I started out that way. That being said, what I'm going to do is I'm just going to close the class out for the rest of the day here. I may post a couple work problems for you to do, just to get you in the idea of how to calculate work problems. I'll keep them a little bit simpler than what we just did there. Just be prepared that you may see something with the next couple of days. I might post a couple problems just to work on, that you can work on for Monday, over the idea of work, just to reinforce what we talked about previously with respect to work and how to calculate the work. I apologize for the difficulty of the problem, what we just did there. We'll eventually come back to that type of problem. We'll be able to achieve that a little bit easier as we move forward through the idea of work here. Once again, look for a couple problems I may post on Classroom for you to do. I have to get to a meeting right now, so I'm going to close out the class for the rest of the day. Look for a couple problems maybe that I'll post on Thursday or Friday in the physics Google Classroom, just for additional practice come Monday. Questions you have? Okie doke. I'm out of here. We are done for the day. You folks have a great day. See you later.
Thanks, you too. Thanks, Mr. Gregory.
Yep.